Okay, now it's 5 minutes past 2 o'clock, and I want to introduce you to our next speaker. The next speaker is Kevin Pouls. Kevin is a scientific researcher at the Fraunhofer Institution for Battery Cell Production, and his speech today will be about the role of digitalization within battery cell production or battery production. We're very happy to have you here and quite interested in your talk. The stage is yours.
Well, thank you for the introduction, Thomas. As you said, my name is Kevin Pouls. I'm working in our digitalization team. And most of you might have seen this graph, which shows the forecast demand for lithium-ion battery cells. And the graph for volume of data created worldwide looks quite similar. And both of these topics have a lot of research going on. There's innovations happening every month. And we want to look at how we can use this to make use of data in battery cell production, how we can combine all the exciting things happening in data science and help them to innovate lithium-ion battery cells. So who are we? Our digitalization team consists of 3 groups. First, there's data acquisition and aggregation. They're trying to answer all the questions around how can we digitalize our machinery, how can we gather the data, how can we pre-process and process large amounts of data? Should we do this with edge computing or cloud solution? And how can we store this data to have it usable for other use cases? And then next, there's the database improvement of production. We're looking at how can we use the data we gather to improve production, for example, with data science tools, analyzing it, gathering new insights, or building machine learning models or AI to improve the production. And lastly, there's the digital factory and production planning. They're looking at how can we digitalize the factory planning, and also if we need to remodel or change our production lines, for example, using the building information model. And then how can we use this model to also improve production planning with simulations? And there's some topics which involve all the groups, which are, for example, digital twins, all the models and systems and how they interact with each other, and also with the physical assets, and how we can integrate them in a battery production. And then also there's the battery passport, which will need input of all 3 groups. We want to establish additional value and sustainable battery production. And we want to do this for and with partners. And for example, we can do this by developing new approaches for digitalization and database optimization in research projects. So how are we going to do this at the FFB? As you've heard before, we have 3 steps: the workspace, the prefab, and the fab. And we want to digitalize all of them. So we'll have 2 fully digitalized factories with the prefab and fab. And here we can test our infrastructure and composed of building blocks. These blocks could be standard interfaces, data standards, models, digital twins, and also simulations and AI models. Now, these building blocks, some of them will be our own developments, but we'll also test and evaluate existing solutions and try hybrid solutions. And then having a digital infrastructure, we can be an enabler for both internal use cases and our partners. Obviously, we want to bring this knowledge to the industry. So we also want to focus on how we can use this to bring it into industry. And this would be by simply transferring some of the building blocks or adapting, extending them, developing new ones. And the creation of standards will also tremendously help adoption. And then we also want to use our infrastructure to validate partnerships from small to gigafactory scales. Well, to summarize, we want to build 2 fully connected digital factories, and based on our mistakes, we want to help partners to learn from our lessons learned. And one of the key technologies we identified would be digital twins. We see them as enablers for digitalized battery production. What is a digital twin? I'm starting with this quote. A lot of you might know it. When Apollo 13 had problems, and used a physical twin of the model of the spacecraft was used to recreate the problem and then find a solution. This is obviously very time consuming. It's still being done today just because the physical models are there for testing, but it's not feasible for all things. So NASA quite quickly thought we can use the digital model, and was made possible by cheaper hardware for data storage and computational power, as well as just more data being generated. And then after this, a lot of industry started looking at it as well. And the digital twin in production was made possible. And you can see that lately the number of publications is just increasing rapidly, which mention digital twins, and it's a big research topic for universities as well as industry. And we want to look at how we can use the digital twin in battery cell production to aggregate data and have it function as a membrane between physical assets and database services. For this, just building one model of the whole factory would be a big task, and it also would limit the ways how we can move this model into industry. So we're splitting up our twin into 3 streams: the building twin, the product twin, which also includes all pre-products, such as the coil or the slurry, and the machine twin for each machine we use. And each of these will be tailor-made for their own use cases and enable different things. For the building twin, this could be virtual factory tools, construction monitoring, as well as integrated facility management, including energy optimizations. And we can use it during the planning of the factory or also during the planning of remodelings. The product twin can be used for traceability, and the battery passport can be used to just visualize the product to help people understand what's happening. We can control and forecast quality, and we can also use it after it left the factory by storing certain information, which helps to optimize recycling. The machine twin can be used for virtual demonstrations, so people can actually get to know the machine before it's there. We can use virtual commissioning to decrease ramp-up time, look at adaptive production and predictive maintenance to decrease downtime. So what would be some external factors motivating people to implement a digital twin? 2 big ones are visualized here. It's the life cycle assessment, which becomes more important because consumers are getting more concerned with the environment and looking at what they're buying and what impact it has. And it's a norm method to quantify the impacts, but the problem is the data collection is very time consuming. And the battery passport is an EU guideline and will be mandatory for certain batteries. The technical realization is still in development, and in both these cases, having a digital twin of the battery would be very helpful because we already have all the data available, and it should speed up the implementation of both these things. And now I want to just highlight one of the use cases we're looking at for digital twins, the virtual experiments. Right now, the questions are, how can experiments be planned with as few resources as possible, and how can we get the greatest possible information content from these resources? The problem is that the battery cell manufacturing process is very complex, and we have a lot of different steps and parameters we need to take account of. And as well, the material cost is really high, so just running experiments would be very time-consuming, very expensive. So there's 2 ways we can improve this. We can first look at which parameters should we run to get the most information possible. And then once we have a good data set, we can start predicting the quality of the output based on the input parameters. This would then allow us to build a model, which is visualized here. We have a platform where we set input boundaries and specify the target parameters we want to optimize. Then we have our digital twin, which consists of physical models and database models, and it gathers data from the machine twin and the product twin. And then we run our models and we get a prediction of which parameter settings we should use for the optimal product. Then we can just validate these with a physical experiment and hopefully just arrive at the best product we can produce quicker. But all this data needs to be traceable because we have to know which settings create which battery. So a traceability is a requirement for many applications we want to look at. What is traceability for us? Traceability means that we can trace all historic data. So no matter what stage the battery is in, we always know where it was produced, what all the measurements were. And then we can also track the future things. So we can use it for adaptive process control and decide what should be done to this product. What are our goals within the Fraunhofer FFB? We want to use this traceable data to identify causes of defects, to reduce scrap, but also to understand why was this defect caused and how can we avoid it in the future. We want to aggregate quality relevant parameters in the digital twins to enable other use cases. And we want to use that for monitoring, so we can always see how the factory is running, how much produces where, how much scrap is generated where, and how we can use this for adaptive process control. What would be one of the main goals of traceability system? How would the traceability system be implemented? Here's how we are looking at it. We want to use data metrics codes for the copper foil, and big questions here: how many data metrics codes do we need? Our plan right now is to use one for each sheet. But then the other thing is, how can we mark these? Should we use a laser-based system? Can we use an inkjet printer? Are there maybe marking-less technologies we can use? And if we have to mark something, how would it affect the battery chemistry? And then once we decide this, we can start gathering all the data, take all the parameters of slurry, link it to this code, gather all the surface inspections, thickness measurements, and then all link them to this code. So whenever you enter this code in our database, you can gather all this data until it's all in a cell, and then we have a fully traceable information. And currently in the workspace, we're trying these first two steps. So we want to use a laser to use data metrics codes, so we can make all the process traceable. And once this is done, we want to use this first to research cause-effect relationships. At the moment, all our cause-effect relationships are done by expert interviews, which is very helpful. But sometimes the experimental results challenge these cause-effect relationships, or there's no consensus in it, or its strength. And here, a database approach would be tremendously useful, because we can, by data analysis, validate, refute, or extend these relationships. And we can also use it to quantify the influence of parameters. So we know exactly which one we should optimize and what the influences of it is. And we can also look at how these different parameters affect each other, which is just very hard to do by human knowledge, because it's such a complex and long process. Nevertheless, we want to still use the expert knowledge, so we want to combine both for a final cause-effect relationship. And now that we hopefully have all our data traceable and stored in digital twins, so it's nice and structured, we can look at machine learning battery manufacturing. Here we see a lot of potential benefits, and I want to just show some of the use cases we can see and potentially want to explore. The first big part would be machines and assets. We can run simple anomaly detection to quickly identify faults within the production line, so we can stop or adjust the production before a lot of scrap is generated or something's damaged. In addition to this, we want to look at predictive maintenance, which would mean, for example, that we monitor ball bearings, the extruder, or pumps using vibrations, for example, so we can just estimate the wear of it and optimize maintenance schedules. The same could be done for the cutting edges at the slitting machine. We could use here image detection for the edges and then decide when a cutting edge needs to be replaced. Further on, we can explore self-learning machines. And here we want to make it possible that if a machine detects a fault in a product, for example, the coating is faulty, could we teach the machine to adjust its parameters by itself, so no human needs to be involved? The next big topic would be processes. We can obviously optimize process design management and optimize routing and scheduling for processes. Here it's just a lot of options that which interact with each other, so human approaches can never fully understand all of them. Energy optimization includes environmental control, but we can also see if we can schedule processes so we can recuperate as much energy as possible. And adaptive production control is that we want to look if we know exactly what the input is, so we know how the surface is after coating. Can we adjust the calendering based on this so we get an optimal battery? And lastly, the product. Here we want to implement quality control, which can be as simple as just image detection for surface inspections, but also we want to look at if we can use all the data we gather to do more complex algorithms and predict the quality of the future battery cells to decide if it's even worth further processing this product. And lastly, we can also look at product design to see if we can help with data, help to find the best settings for the coating thickness. I just want to lastly highlight one of the, so AI has the potential to increase the efficiency, sustainability. Now, lastly, I want to highlight one of the use cases, which would be quality prediction information. Right now, the problem is that 5 to 10% of cells are rejected at the end of line testing. This is after storage phase for up to 3 weeks. The storage phase will obviously increase its production time and cost. And by predicting if a battery cell will pass end of line testing, we could save the storage space by just scrapping them before. And in addition, we can also look at if we can optimize the storage time for each battery cell, so that it's not a fixed value, but the minimum value for each battery cell. So we want to develop a quality prediction, which uses all data gathered, and then reduce or eliminate the aging step. And the result would be time and cost reduction. And for this, we have all our data gathered in the digital twins, which is traceable. We want to feed this to machine learning algorithms, which first predict will it pass end of line testing, and then predict estimate how long does it need to be in storage. And the result would be a time and cost reduction. And the key takeaways from this presentation, which we'll hopefully gather, is the digital twins are a key enabler for our digitalized production. Traceability is needed for many use cases and allows for new process insights, and that machine learning has various applications in battery manufacturing. So digitalization can aid most research topics and is a big research field in itself. Thank you for listening to me, and I hope you have some questions.